Good morning, and welcome to another edition of our Between Two Nerds live stream. I'm Jeff Doyle, member of technical staff at Apstra, and you probably know me best as an author of TCP, routing TCP/IP, and a few other books. And with me is my friend Jeff Tantsura. Morning, Jeff.
Hi, morning, Jeff. How are you doing today?
Good. Give us a little introductory spiel about
Jeff
you.
Tantsura. I'm heading networking strategy in Apstra, and you might know me from being here and there. My work in ATF, maybe book, Navigating Network Complexity, we published with Ross. I'm really proud of good reading.
I've been meaning to plug that book for a while. I've got to do a better job of that. We've got a copy of it around here somewhere and can't find it. I may have loaned it to someone, but one of the best books, whether you are a beginning networker or whether you're an experienced networker, it basically covers, this is the book that Jeff and our mutual friend Russ White wrote, but basically covers networking basics, but from a completely different perspective. But it's a book that I highly recommend. Managing Network Complexity, right?
Yeah, coming from you, it's an amazing compliment.
Oh, yeah, one of my favorite books. So anyway, today we're going to continue our discussion from our last live stream about BGP in the data center. And when we did that one, a friend of mine on Facebook, Eddie Chan, posted a question that just said, yeah, but what about convergence? Which is always a concern with BGP. And so we both thought that was a great question and wanted to address that this morning. Just to sort of talk about why that's a concern. Probably all of you know this, but BGP is a distance vector protocol, although the distance that we actually use in BGP is autonomous system hops rather than router hops. And so we call it path vector, but it's distance vector. And what that means is that I only know, all the information I know about the network are what my directly connected neighbors tell me. All that they know is what their neighbors tell them, and on and on and on down to whatever the prefix advertised is. So if a prefix changes or is advertised at some distance, I don't hear about it until all my neighbors along that path have received the information, processed it, and updated it along the way. And as a result, BGP converges very slowly. That's not necessarily a bad thing in the internet, which BGP was designed for. We have kind of a trade-off of fast convergence in favor of stability. If it's converging a little bit slower when things are thrashing around, we don't get as much of a flood of information. I'll talk a little bit more about that in a bit. But anyway, that's just sort of where we want to start. And Jeff, beyond that, when we put BGP into the data center, and this is finally getting to what we want to talk about today, there's some adjustments that need to be made, right?
Absolutely. And so we'd like to start, for those who didn't attend last podcast, with the same picture we used to use there. And hopefully we managed to convince you that using eBGP in your fabric is a good idea. And actually, we are going to go to some benefits as to why. So again, we are going to use same topology as before. And ISN allocation scheme here is in conformance with RFC 7968, meaning unique ISN per leaf, same ISN on all spines in the pod, same ISN on all super spines. And we'll come back to the scheme number of times here. So you see goals, and those are really goals to achieve convergence as fast as possible. So what's convergence? After there's a change in the network, when every device has changed their RIB and FIB and installed all the prefixes. So it's from the moment change has happened till the moment everybody has new information and is capable of sending traffic right way. So let's start with how do we detect failure in BGP? As we all know, traditionally, we would rely on BGP hellos, which are by default set for eBGP on 60 seconds with total of 3 hellos. We are talking 180 seconds, obviously unacceptable. Luckily, in data center, in most cases, links are point-to-point. Moreover, today BFD is supported on any platform. BFD is a lightweight protocol to provide reliability. So rather than relying on slow hellos, today we can rely on either loss of signal or loss of light if you use optical interfaces, or BFD. The errors propagated different ways depending on the system. Sometimes BFD is a better solution because state is created directly on the forwarding ASIC, and when BFD state changes, so it goes to down, all the inactive next hops that were registered to this particular IP address are removed. So now you could go as fast as 3 milliseconds or maybe 10 milliseconds with BFD and know about failure within 10 to 30 milliseconds, so very fast.
You mentioned the hello and keep the hold and keep alive timers, and keep alives by default are usually 60 seconds, and the hold timer is 3 times that. Is it still worth changing those? You see a lot of things where they talk about cutting hello down to 3 seconds, which is still way slower than BFD. But is there additional benefit to also tweaking your hold and keep alive timers?
Really not. So keeping it on 60 seconds doesn't make much sense because this number really from the times when we had 200 megahertz CPU on the devices, right? So bringing it reasonably conservative, but you rely on either BFD or loss of signal. So you don't want this to compete. Remember how fast reroute would compete with ATM resiliency. So we don't want to be in this situation. What we want to be reasonably conservative, low interval. So 10 seconds sounds like a good one, and really fast heartbeat on the between devices themselves.
And I was just noticing on the chat window here, my friend, I think you know him too, Orhan Ergan, is actually asking why not fast reroute in the data center, since you mentioned fast reroute.
Great question. So there are more varieties of fast reroute, but specifically here we are talking about things like loop-free alternatives. So to begin with, for loop-free, you need an IGP, you need a link state protocol. But the most important point in technology such as loop-free alternative, usually you have non-CMP paths. So you've got the best one, and the next one, and next one. So what happens in LFA, you take a secondary path that meets some requirements. So we can go through LFA another time. The most important one is loop-free. And then you install it in your forwarding, and when primary path fails, or primary prefix, depending how you do LFA, you could switch over another one. So what's important here is to compute a loop-free path. That's why we call it loop-free alternative. In data center, however, in leaf-spine data center, you've got massive eCMP. So all endpoints are equidistant. And eCMP prefix is per definition loop-free compared to primary one. So rather than using LFA, which is reasonably compute-intensive and complex technology, we use technology called fast rehash, meaning you've got mTRI-like structure on your forwarding ASIC, and when something goes away, you just remove a pointer to adjacency. So if you had a CMP of 8, you might have a CMP of 6. right? So you don't need to pre-compute backup path. It's already there. You just have an mtry structure with all this next hop, and you use local hashing, depending how you do hashing, and you hash traffic across this point.
Yeah.
So fastly hash versus fast reroute.
I think there's an advantage too. I mean, just from the diagram you've got here, it's pretty easy to see. You know, I made that first sort of introduction about BGP, and you know, you could have a lot of hops between you and some updating source, which takes a while to update. But the very fact that we're using BGP in the data center along with the CLO architecture, you can look at, you know, at least for the three-stage architecture that you have, you know, in either one of these pods in your drawing, there's no, every single leaf is exactly 2 hops away from any other leaf within a 3-stage. And so that in itself, wouldn't you say, also contributes to less convergence concerns, because there's not that many paths to update across.
Absolutely. We are going to take so we are moving to the update as fast as possible. So we don't want a switch try to use another path and yet another path till everyone converges. It's a phenomenon known as path hunting, and we're coming back to the ISN allocation scheme we advised you during the last podcast. So if we look at spine in IS 65001, they're in the same ISN. What it really means that the update that's coming from every leaf connected to it it will actually go back to all other leaves because they need to know where you are, but it won't go back because spines will drop it due to IS loop prevention. So what it really means, if you from spine perspective, if there's a server connected to one of the leaves, you will have single route. If it disappears, you can immediately react on it and send updates up towards the super spine. So very fast, no path hunting. If you look at prefixes that's coming from another pod, you will have a ECMP set with number that is equal to fan out of your super spines. So in this case, if it disappears, nothing has changed. You can still reach your super spines, right? So in this case, you just need to change your hashing buckets, and this again, fast rehash. And if this path used to be the best path, you would update routing by implicit withdrawal, which doesn't really impact forwarding. Or if it wasn't, you don't need to do anything. You can still reach anything in pod 2. So if failure happens between a particular leaf and particular spine, you don't need to know. So BGP gives us great ability to mask these failures because of the structure where all the traffic should always go up in order to go down.
Yeah. Yeah, and one of the bullets that you've got here that that I wanted to mention, you're talking about propagating failures as fast as possible with MRAI timers. That's minimum route advertisement interval. I think I can never remember acronyms, but it's basically the neighbor update or advertisement interval, which again in the public internet is maybe set to like 30 seconds, which means, you know, if there's a lot of thrashing in the network and things going on, and you get information to update or withdraw routes, basically that says wait about 30 seconds, and you can both pack your update more with information and maybe have less flooding to your own neighbors for updates. But we certainly don't want to do that in the data center. And so one option, if it's not already set by default, is to set your neighbor advertisement intervals, or MRAI, down to 0, which just means don't do what you would do in a service provider network. In the data center, go ahead and update your neighbors just as fast as you get information, because you're obviously not dealing with enormous, multiple hundred thousands of routes in a data center like you would be in the public internet.
Yeah, so pay attention to that. Some implementation will allow you to say it by macro, like on Cumulus. Some will require explicit configuration to set MRI timer to 0. In data centers, definitely recommended setting.
Yeah. And I'm just looking at my timer here. We actually are out of time. It's 10:30 my time, but we've hit the 15-minute limit. And there are a few questions that we have over here that unfortunately I don't think we really have time to get to, because some of them will take a while to answer, but maybe we'll continue this topic at
absolutely. BGP convergence is a fascinating topic, and I think we will pick up next time, hopefully next week, where we'll today. There are many things to discuss.
Absolutely. Okay, well, to all of you that joined us, thank you for joining. I hope that this session was useful. And please continue to join, and we will continue to come up with some interesting topics to talk about.
Thanks, everyone, and take care. Till the next time.